Yeah, so thank you so much for that introduction. Hello everyone. Thank you for joining us today. My name is Shoshauna Gauvin, and I'm a theoretical physics graduate student at the University of Waterloo. And today's presentation is going to be on the topic of gravity, entropy, Ricci flow, and Perelman's W functional. So, gravitational systems have long been perceived as intrinsically thermal, a perspective that's pioneered by the seminal works of Bekenstein and Hawking that revealed black holes possess both temperature and entropy. In this presentation, we're going to build on this to try to reveal a deeper connection between thermodynamics and gravitation. Our mission is to demonstrate that the evolution of gravitational systems, and in particular black holes, can be understood as thermodynamic processes. And we aim to present these advanced ideas in a fairly simplified and more accessible manner for the broader audience. And so for the more dense mathematics, you can instead refer to my pre-published works and references that I provide at the end of this presentation. So this is how the presentation is going to be structured. We're going to start with some background literature, delve into some new standard insight, and examine some of my core hypotheses and some novel results that I think I found. There's going to be ample time at the end of the presentation for questions and discussions, so I'm going to ask that we hold those questions until the end. So, a major criticism of deriving physics from Fisher information is its inherent flexibility, manifested this from the freedom to choose various ad hoc constraints or parameterizations. And this kind of renders the framework capable of reproducing almost any physical law, but the malleability raises concerns that where people pursuing this are more retroactively fitting known results rather than being able to predict new phenomena. And this is very understandable as a concerning claim. Because Fisher information is sensitive to the choice of the coordinate system and lacks a unique invariant formalization, this approach risks to being overfitted or unfalsifiable. And this kind of compromises its explanatory power as a universal physical principle. Specifically, I address this criticism of excessive flexibility in Fisher information by trying to anchor my framework within a physically motivated constraints. And I do this by enforcing a dual affine geometric structure and maximum entropy production principles, alongside stringent dynamics that are dictated by Ricci Flow and Perelman's functions or functionals. And this approach, I hope, restricts the degrees of freedom to only those solutions consistent with gravitational relaxation, causality, and thermodynamic equilibrium. And this, hopefully, we can see will prevent arbitrary tuning and ensure that my predictions are both clear and testable. So, building off of Jane's principle of maximum entropy, which was derived in the 1950s, the probability distribution that best represents our current knowledge of a system is the one with the largest entropy. Wang et al. In 2007 demonstrated that the path that satisfies the principle of stationary action, which I'm sure we're all very familiar with, can also be viewed as the one that maximizes entropy, making the least action path the most probable in the information space. Formally, this appears as the probability of the path is proportional to the exponent of the action term. And so when we have a large eta term, this forces the action term to be minimized. And this is akin to the Feynman path integral construction, where if the action is not minimized, you get too many divergent terms that all cancel out. And so from this approach, we can reconstruct the Euler-Lagrange equations and even connect emergent gravity ideas with quantum relationships like Schrodinger and Dirac through like minimization principles. And in essence, the principle of stationary action aligns with a worldview where maximum entropy production principle. So those two can kind of be seen as equivalent. And something that many of you are probably familiar with, and then since you're all information physicists mostly here, I view Shannon entropy as the optimal measure of how many bits of information are kind of needed to encode outcomes of a given probability distribution. And in that, the callback Leibler divergence is then kind of seen as a penalty or an extra cost from switching from one distribution for that encoding to another. And so KL divergence kind of captures how one distribution diverges from another and fundamentally builds upon the concept of Shannon entropy. And by treating KL divergence as a generating functional, and we do the second order expansion, this is actually how we get the Fisher-Rao metric, which is the unique metric for the Riemannian informational manifold. And extending this expansion to higher order terms, we reveal additional geometric structures, such as the skewedness tensor. And this can kind of illustrate how the broader framework of information geometry, we leverage these like cost functions or these divergence functions as a measure of distance to uncover the local geometric structure of the distribution space. And so something that might help some of you is imagine you're trying to compress a message so that it uses the fewest possible bits. Any extra bits represents an inefficiency or redundancy. I mean, you can kind of think of this as like the Kolmogorov complexity. And so in the same way, a gravitational system that isn't in equilibrium carries excess irregularities in the curvature. And Ricci Flow, which will be introduced later in this presentation, acts as a natural compression algorithm for spacetime. And this gradually smooths out those irregularities, just as an optimal encoding scheme removes redundant bits. And so both processes are driven by the idea of reaching a state of minimal waste. And so efficient coding eliminates the unnecessary information, while gravitational relaxation minimizes excess curvature and energy, guiding the system towards a stable equilibrium, which is a maximum entropy state. And so a much more like heuristic or, maybe playful example is you can imagine a fresh, undisturbed field of snow. Now we can consider that we come across this and we see a single set of footprints imprinted in that snow. These individual tracks carry a rich, detailed information. They're going to reveal the direction of the person traveling from the orientation of the footprint, the speed from the depth or the amount of displaced snow, and even details like the stride length can be determined. And here, the divergence captures this extra information or the surprise in observing this distribution when compared to the expected distribution. And now, instead, we can imagine tens of thousands of people walking on that same path. Their overlapping tracks eventually blur all individual details out, and the compacted snow kind of erases all those unique features, and any individual single set of footprints kind of gets blended away. Eventually, the snow surface becomes uniformly marked, and the individual variations all vanish. And in this state, the distribution of tracks becomes highly symmetric and uninformative from an individual perspective. We can only really get like mean average information. And this corresponds to when the divergence is essentially equal to zero, and which is the maximum entropy state where P and Q are both equal. And this analogy, I hope, kind of illustrates that when two distributions are identical, there's no additional information or divergence between them. The dual affine geometry emerges naturally from this divergence function through its local expansion of that probability manifold. When I expand divergence function up to the second order around a point, the quadratic term defines that Fisher information metric, which measures the infinitesimal distance between nearby distributions. But because the divergence function is not symmetric, in other words, P relative Q does not equal Q relative to P, differentiating this in respect to the first argument versus the second yields two different connections. And these two affine connections, usually here denoted nabla and nabla star, turn out to be dual or at least conjugate in relative to the Fisher metric. And this means that one connection naturally pairs with the other, often through the Legendre transform. And this reflects the convex duality that's inherent in this divergence function. And so in a dual affine geometry, we have two distinct yet flat affine connections, each with their own geodesic that's linked with the Legendre duality. And because each connection gives a different path between the points, they capture different perspectives on the manifold. And this distance or this difference between the two connections is governed by the skewedness tensor, which is, you can see down below, it's this alpha divided by 2 with the t, that's the skewedness tensor. And in many applications, such as information geometry, these dual connections relate to how far from equilibrium the system is. And so an interesting byproduct is when these two connections are considered self-dual, there is no skewedness tensor, or there's no skewedness tensor contribution, and the Levi-Civita connection emerges, which is the standard connection that we usually see in differential geometry and general relativity. And then this is kind of seen as a special case. And we can say that the equilibrium, or the system is in equilibrium when there's no independent path-dependent processes underway. So when I consider the divergence, which measures the inefficiency of approximating P with Q, it forces Q to assign a non-zero probability. And so this means that if P has multiple modes or multiple peaks, Q must broadly cover all of them to avoid infinite divergence. In other words, the divergence of PQ exhibits a mean-seeking or mass-covering behavior because it averages over all of P's mass. On the other hand, the divergence of QP penalizes Q for assigning probability distributions to regions where P has little or no observation. And so this minimizes the divergence to concentrate Q on the most prominent modes of P. And this is what we call mode-seeking behavior. And when the overall divergence vanishes and the system is self-dual, this is what's governed by that Levi-Civita connection. Every mode in P must be perfectly covered by its counterpart in Q, with any residual discrepancy being exactly accounted for by an intermediate distribution. And in practical terms, this means that in order to have zero divergence, the approximation must capture all independent features of the distribution with no leftover error. And that means the subdistributions themselves have to be symmetric and in their own maximal entropy state. And this is kind of, I know, I like this graphic. Kind of illustrates the mode-seeking behavior. But a heuristic example, say you're a professor of physics and you have a class. You must choose, do you teach the average student or do you teach to the higher performing students? No matter what you choose, there are going to be implications to this choice. If you choose to focus on the students with the greatest potential, naturally some of those weaker students are going to drop out and become engineering students. Obviously, I'm joking here, but I apologize in advance to any of the engineers in the audience. Minimizing, the net divergence here in dynamics essentially means that the system is working to balance out a global mean-seeking pressure with a local mode-seeking drive. And as the difference between these divergences decrease, the dynamics push the system towards a state where neither tendency overly dominates, and this leads to a balanced maximum entropy state. And in practice, this balance manifests as the system gradually smooths over sharp discrepancies and ensures that the overall distribution becomes both adequately spread out, but also faithfully concentrated on key features. And this achieves that stable equilibrium. And so one of the takeaways that I'd like you guys to think about is, in this way, maximizing the entropy, which minimizes the net divergence, is akin to optimization function. This process ensures that all resources are used optimally, and the mean-seeking behavior guarantees that all regions are adequately covered, while the mode-seeking behavior focuses on the most significant peaks. And this balance corresponds to achieving a maximum entropy state, again, which the redundancies and inefficiencies are minimized. So a dual affine geometry naturally encodes this multipath dependence, which is crucial for optimizing problems. By taking the advantage of this fully dually flat structure, we can balance global coverage with local concentration, kind of ensuring that we navigate a space of possibilities efficiently. And so much like a robot trying to adjust its trajectory in changing coordinates, this approach is driven by the principle of maximum entropy and promotes the exploration of available outcomes while remaining computationally feasible, is one way you can think of this. And so this is essential because in almost all geometries, we don't have a smooth or yeah, a smooth manifold, whether we encounter unexpected surplus curvature, bumps and wrinkles, or dealing with elastic systems, such as this image here of a robot traversing a rope bridge, whose dynamics are going to inherently change as a result of the crossing. So in general relativity, or more broadly differential geometry, we already have this concept of path dependence embedded in curvature. On a constant curved surface, parallel transport depends on the path taken. And the classical example of this is taking a closed loop from the equator, the North Pole, and back down to the equator, then you travel down along the equator back to my origin. And because of curvature, you're going to experience a net rotation in your vector or your orientation. If you trace that path backwards, you're going to reverse this rotation and return back to origin. However, physical systems don't behave in this way. If we imagine that this globe is not the Earth with a kilometer of crust supporting its weight, but rather it's a giant bouncy ball that we're traversing, one can imagine that the resulting net rotation will depend not only on the starting curvature of the object, but also complex interplay between our weight, the surface tension, and the pressure dynamics with the ball and the speed that we travel. And in this, I argue that we can't simply examine gravitational systems through a single path dependence. In a standard Riemannian manifold, the parallel transport around a loop often sums to zero or no net harmony. And this no net refers to the overall rotation of a vector experiences when it's being parallel transported along the closed loop in both rotations. So you go in one orientation rotation and then the opposite. And essentially, this measures the cumulative effect of curvature or the connection of the space on the vector's orientation. However, on an information manifold with dual connections, with a non-zero skewedness, the path matters beyond just the geometry of the shape, because we have a non-symmetric distributions that encode directional bias into the system itself. And so this can be seen almost as the arrow of time. The system evolves under an entropic dynamic, and the built-in asymmetry manifests itself as an irreversible gradient flow towards maximum entropy. And this defines that arrow of time, which is not present in a regular differential geometry or GR perspective. And so for the International Space Station orbiting the Earth, Earth's gravitational potential completely dominates its local environment, effectively making the system self-dual. The station's dynamics and surrounding geometry are governed almost entirely by Earth's field. However, in a system like a black hole tearing material off to form an accretion disk, the skewness tensor in the dual affine geometry would become critical in determining the dynamics of the system, and this reflects the non-trivial independent path dependencies. And this differs from the Veal tensor in general relativity, which governs the tidal forces specifically and the shape of space-time. So in other words, the dual affine skewedness kind of handles how far we are from a maximum entropy state, while the Veal tensor handles the actual curvature gradients, kind of tearing that star apart. And so the takeaway from this, we can reconstruct the principle of stationary action via entropy maximization. The sensitivity of a parameter is defined by that Fisher metric. The dual affine geometry captures multiple path dependencies, and the skewedness tensor provides equilibrium information. And so we can store this away as we get into the next topic or the next piece that's going to be needed, which is Ricci Flow. And so Ricci Flow shows how the metric G evolves over time, driven by curvature. Here in this image, you can imagine some perturbed geometry returning back to a spherical solution. Much like heat diffuses through a solid, smoothing out irregularities and guiding the geometry towards equilibrium. This process can offer a thermodynamic perspective on how gravitational systems evolve, and this ties directly back into our self-dual condition, where the dual affine geometry evolves towards that equilibrium state. I often encounter lots of people in theoretical physics and whatnot that talk about Ricci Flow as just some mathematical tool, but like, what does this have to do with physical systems? And it's already currently used in many different applications in engineering and otherwise. And so I just want to point that out and avoid that question later. And so Who is Grigory Perelman? So he's the man who refused the Fields Medal. He refused the $1 million Millennial Prize for solving the Poincare Conjecture. And he's refused numerous tenured professor positions at prestigious universities. And he currently lives in his mom's basement in Russia, I believe. Um, and in 2006, Perelman's papers were submitted on the archive. And he introduced the entropy formula for Ricci Flow, a surgery method to handle topological changes, and a finite extinction time result. And together, these three papers have been determined to have solved the Poincare conjecture and show how Ricci Flow can manage singularities on three manifolds. And so Perelman's W and F functionals quantify the entropy or energy that's stored in the manifold's curvature compared to the current geometry to like an equilibrium soliton. And these are monotonic under Ricci flow, meaning that they decrease in a controlled way and help track how close or how far the metric is from a soliton solution. Tau represents an intrinsic timescale over which the system relaxes towards equilibrium, and this is analogous to the thermalization time. And in many contexts, as tau increases, these irregularities smooth out as entropy increases, indicating that the system is thermalizing or approaching some maximum entropy or steady state. And so here I have the framing question for the audience. Does gravitational potential relax globally instantaneously with a spatial propagation speed of the speed of light? Or is metric relaxation inherently a local Planck scale constraint, and it's constrained by causality and evolve in a Ricci flow-like process? So in space-time, curved space-time, our notion of volume and distance is fundamentally tied to a redshift factor. This tells us how lengths shrink as we move between different regions or different curvature. And this means even the Planck length, universal constant, effectively varies with position relative to an observer, since the redshift directly rescales the characteristic length, scales that we use to measure volumes. And this is why in cosmology we don't use a measure of length or distance, but we use redshift. And in this diagram, you can see that the circle on the bottom left there represents the source of curvature, which generates a gravitational potential. The boxes on the right are kind of these layers of infinitesimal volumes separated radially. And so from an observer situated at infinity, this demonstrates the change in potential energy and effective variation at that Planck length. And so here I present a dynamic scenario where two point sources are merging and separated by some infinitesimal step. The resulting convergence causes the surrounding geometry to evolve in real time. And these concentric contours and vector fields show that how the gradients themselves shift as the sources converge. And the image on the right is my best effort at illustrating the changing curvature on how local fields respond to emerging potentials. I should state now, just to set expectations, that my artistic skills are quite limited. So this is kind of the best I can do. Here I show Ricci flow equation acts like a relaxation process that can be viewed much like a diffusion process in geometry. The diffusion process on the metric is exactly more precisely. And this gradually smooths out curvature, making it more uniform. And so if you take a baseline metric and introduce some small perturbation, and then we decay this exponentially according to the flow equation. By applying the Turk trick, this flow becomes strictly parabolic and similar to a heat equation, so that each eigenmode effectively smooths out over time. And this illustrates how curvature naturally diminishes, driving the system towards a stable state of equilibrium. And we can then now look at this eigenvalue problem from a bounded potential, where we talk about the maximum relaxation rate. We're specifically talking about the bounding of that value of the eigenvalue. So the next section here. So here's my onset is that I propose that the decay rate, the eigenvalue that's bounded for the Ricci flow for the metric relaxation, is capped by causality, implying spacetime can't relax faster than light speed constraints. In extreme events, like a strong field or near a singularity setting, this bound ties the Planck length to the maximum rate of which curvature can dissipate. The left equation is kind of a proposed limitation on maximum redshift change for an infinitesimal coordinate step. And on the right is more a generalized statement that a photon with a high certainty of position has an uncertainty in its position at a time plus one Planck time relative to the Planck sphere, right? And so here is more of a purely illustrative example, not a direct one, but we can imagine how waves experience extreme redshift under a high gravitational field. If we don't want some like discontinuous wave function, the wave relaxation should be bounded by some kind of fundamental limit, tying their changing wavelength to the Planck scale. And we should be able to observe this effect in some kind of extreme scenario. And the maximum energy relaxation is shown by this delta E bound. And it's interesting to note that the Hawking characteristic wavelength is proportional to the radius of the event horizon. And this gives us a potential candidate for kind of examining the dissipative forces at the event horizon. So when would this ever kind of happen? So here's some extreme, if not maybe slightly implausible events, but say we can have a singularity that's moving through some diffuse gas cloud. If the relative velocities approach the speed of light, while highly unlikely, we would expect some extreme gradient waves in front and in behind of that singularity, potentially reaching this threshold. The second example is a more realistic scenario is two rotating black holes that are going to collapse in on each other. As they collapse in, their velocities start increasing. And similarly, we should see extreme gradients from that kind of behavior. To get a better idea of what this means when integrating Perelman's work, we can compare the baseline geometry, which is this solid line, to a perturbed geometry, which is the dashed line, showing how changes in the underlying geometry can shift the effective potential. And here I'll also note that the cubic form, which comes from the skewness tensor of the dual affine divergence, is also an effective measure of the area between these curves, giving us yet another example of how these two frameworks overlap in examining non-equilibrium dynamics. And so the area between these curves represents the excess potential resulting from these geometric perturbations. And it should be clear that this illustrates how seemingly minor alterations in a geometry can translate into noticeable differences in the energy profile and curvature gradients. And this reinforces the idea that the microscopic geometric variations can have a macroscopic dynamical consequence. So now if we have a scenario where the maximum relaxation is reached, say at the event horizon, there are some very intuitive implications. Here I illustrate how the curvature of spacetime outside the black hole's horizon rapidly relaxes into a kind of soliton-like equilibrium state. And this is because the vacua kind of acts as this ground source for this potential and is free to dissipate as we would expect and predict from general relativity. So what this means is that despite any extreme curvature that might exist internal to the event horizon, the external gravitational field is completely determined by the net flux of curvature through the event horizon. And so the event horizon acts as a critical boundary. It sets a cap on the gravitational influence because much like Gauss's law for gravity, the total curvature flux through the horizon is directly proportional to the surface area. In practical terms, even if the interior of the black hole does vary wildly with an extreme curvature, an outside observer will only detect the gravitational field that corresponds to the area-dependent flux that passes through the boundary, which again, we are hypothesizing that has some maximum boundary that has been reached. And this explains why we can't infer an internal structure from a black hole from an external measurement. The horizon fundamentally limits what can escape. And to inform our what will inform our observations. And so this perspective isn't a very common or standard in black hole literature, but I find it conceptually very intuitive and revealing to understand how gravitational forces, such as lensing effects, are governed by the horizon's properties. So here I'm going to just introduce briefly the concept of thermalization time. Essentially, this is the system's relaxation time by reaching equilibrium, and it's not only reflected in the exponential decay of the system's temperature towards equilibrium temperature, but it's also a way for Ricci flow to smooth out curvature irregularities. And just as thermalization in physical systems is determined by how quickly local imbalances decay, which is related to the inverse eigenvalues of that governing operator. Ricci flow thermalizes the geometry by diffusing away curvature effects over a characteristic timescale. And most notably, Perelman, his tau variable is precisely defined as a backwards evolution and acts as a reverse running clock or an inverse temperature clock, capturing how the system cools down and settles into a steady state. And this unifying notion of thermalization provides a geometric analog to the physical relaxation process. And in contexts like black hole physics, tau is linked to phenomena such as the quasi-normal mode decay and Hawking radiation. By interpreting the evolution of black hole geometry through Ricci flow, we can view Perelman's tau as a characteristic thermalization time and the clock over which curvature irregularities dissipate. And by doing so, we can tie this process to a physically observed process to ground us and to avoid arbitrary constraint imposition. And in this picture, Hawking radiation emerges as a manifestation of the geometry's relaxation process, where diffusion of curvature towards equilibrium corresponds to the energy loss via this thermal radiation. And so here I'm showing how Perelman's work informs Ricci flow behavior near the event horizon. Under Ricci flow, the metric often separates into a cylindrical product structure, where the cross-sectional directions focus the curvature, forming the narrow neck, which is the event horizon. But the axial direction remains nearly flat, and this is because there's no stretching force in that direction. And this stands in sharp contrast to a true singularity, where the curvature would blow up in all directions, leaving no flat region at all. But according to Perelman's framework, which solved the Poincare conjecture, there's also this maximum relaxation bound at the event horizon. And this acts like a dam that keeps curvature from dissipating outward too quickly. And as a result, curvature inside surpasses the naive estimates and accumulates in the characteristic 1 over r pattern or a flat pattern. And this reflects both entropic and energy constraints that fundamentally prevent what's called the K non-collapsing. And ultimately, the horizon geometry itself imposes these limits and ensures that the flow curvature remains consistent with overall conservation laws. It may be interesting to note for some of you who are interested in cosmology that there's a well-defined pyramid Ricci flow structure that's established and well published, which essentially relates how concentric stacked singularities form a pyramid-type object, where the region in between each singularity, we would observe a flat space-time. And so I'm just going to leave that there for now for people's thoughts. So this graph here shows how a bottleneck at an event horizon can force most of the relaxation gradient into a thin boundary layer, leaving the interior nearly flat. And so if the system could diffuse curvature more uniformly, we'd see a smoother drop-off, like a conical or 1 over r profile. But if we have a truly strong boundary condition, while it's not truly discontinuous, it would, almost quite look like that, like a very sharp S-curve shape. And this would form this near constant cylindrical interior with a sharp transition at the boundary. And I also want to point out that a singularity isn't necessarily required in this picture. As spacetime contracts, the Perelman functionals, the W and F functional, increase proportionally and providing this kind of feedback mechanism that prevents an uncontrolled collapse. And any distortions that do arise are rapidly smoothed out by Ricci flow up to the point where the maximum flow rate has been reached. And this helps maintain the near constant interior and the sharp boundary condition at the horizon. It's important to note here that despite maybe a more novel interpretation of black hole thermodynamics, we still retain everything from the area laws. So the maximum flux perspective still retains all those existing observational data. The famous Bekenstein-Hawking result with the entropies equal to area divided by 4 remains valid. The surface area caps the curvature flux, and so the black hole's entropy and energy flow, and thereby the thermalization or the radiative gravitational potential, are directly tied to that horizon area. And this reaffirms the well-known area law for black hole thermodynamics, while potentially providing additional insight into some of the black hole paradoxes that kind of plague our current understanding. And if we wanted to complete the black hole thermodynamics picture in a standard Schwarzschild black hole thermodynamics, the temperature and horizon entropy yield Ts is equal to mass divided by 2. But this omits any kind of curvature entropy or informational entropy from within this black hole structure. And so from a geometric perturbation within the event horizon, if we include those terms and we assume a conservation of energy within the event horizon, minus any of the radiative terms, we should get an extra term of the Ts of curve, which should be equal to the thermal contribution. Yeah. Oh, yeah. So here I would just try and give maybe a more intuitive insight into how these paradoxes can potentially be resolved. So the Bousso-Penrose paradox arises from the tension between two ideas. On one hand, the Penrose's wheel curvature hypothesis suggests that in the early universe, with the Big Bang, we had extremely low gravitational entropy. Whereas on the other hand, Bousso's covariant entropy bound implies that singularities, like those found in the black hole, should have a maximum entropy given their high curvature. And this is a direct contradiction. However, if we model this in the way that I just did, we essentially treat this evolution of the curvature as a smooth, regulated diffusion process rather than an uncontrolled blowup. And in this framework, the formation of the singularity is reinterpreted as a system reaching a maximal relaxation bound, and the state of which curvature is still high, but is constrained by those functionals. And so, yeah, this kind of gives us maybe a more intuitive understanding of why this paradox can be resolved. Similarly, for the information paradox, arises from the conflict between quantum mechanics and semi-classical description of black holes, provided by general relativity. And so, according to Hawking's analysis, black holes emit a thermal radiation. And if this radiation is truly thermal and carries the no information, then the black hole evaporates completely, and we have this loss of information essentially. And I think that this idea is also accounted for when accounting for the informational description of the curvature itself. Okay. So my hypothesis here, before going forward, is that Hawking radiation can be modeled as a Ricci flow relaxation, and by doing this, we should reveal causal limits at the event horizon. So in order to model this here, we can say that the curvature relaxation rate is saturated at the event horizon, and so the decay function is proportional to the surface flux, and Ricci flow time is the inverse thermalized time. And so we just get this kind of standard equation here. So stable black holes should settle into a conical or cylindrical shape, and so their total curvature entropy should be a function of its volume and the slope of this conical structure. And so with this, we can simply set the radius to the Schwarzschild radius for the black hole horizon and get this result at the bottom. And we have this result, which is we have also the well-known Bekenstein-Hawking radiation formula, and which is derived from the first law, or dE equals TdS. And we simply factor out the mass loss, and we should get this below equation. And from two separate papers, I demonstrated that the form of which we should expect a quantum correction from a dual affine geometry from some kind of non-equilibrium dynamics should take this form. And so in other words, the affine connections are separated by some interference or noise correction, depending on how you construct or interpret your data here. And so here we'd have like S dt divided by dV is equal to the negative of T ds by dV, and then some quantum correction term. And obviously in an equilibrium state or an idealized gas state, these correction terms would just be equal to 1, and it would go away. And so we expected either one of these kind of results, and our result is down here on the bottom. And again, the Hawking radiation comes from the form of the first law. And so we should investigate this a bit further. Stable black holes, if we're evaluating a stable black hole where there's no new net flux of energy entering through the event horizon, we can say that the total uncertainty of energy is proportional to the total uncertainty of the measurement of the free energy propagating away from the event horizon. Because the only change in energy of these systems is that thermalization energy that's leaving the system, or the Hawking radiation. And so, as such, we examined the correction terms independently, and in doing so, we find this variable c of mu, which is just the c constant adjusted for SI relativistic units here. And so, some of you may notice that this can be re-expressed as essentially 4 times the Planck sphere volume per Planck time, which is almost exactly what that onsat was at the beginning. And kind of a bit of a shocking result when I first came across this. And in natural units, this actually reduces a bit further and is expressed exactly as the flow rate of the length squared and is basically proportional directly to g, which corresponds to the causal boundary on the eigenvalue for those relaxation modes that we talked about at the beginning. And as such, we can kind of rearrange the original formula to clearly demonstrate that we have this dimensionless ratio here. So it may interest some of you that near critical points where a system often exhibits self-similarity, power laws are very common. And so scaling laws emerge naturally in such regimes because there is no intrinsic length or energy scale, meaning that the temperature and entropy or other observables relate to simple exponents. And the presence of a conformal invariance or renormalization group fixes points and leads to power law behaviors. And this final expression here exactly takes the form of a power law of the form T is proportional to s to the power of x. And the equilibrium we would expect that x is equal to 1. Which relates to the isochoric process, i.e. the process where the surface area is stable or the flux is stable. And some of you may relate that this is essentially describing a state in hydrostatic equilibrium. And so if we take a covariant formulation of this, we can obviously dt d tau is the Lorentz factor. We can convert this to out of the lab frame here. But we'll notice that the volume term or the scaling function should have also some gamma term in the orientation of some velocity. So these two gammas on either side end up canceling out. And we are left with this equation down here at the bottom. And this derivation kind of recasts, SDT, dE purely in terms of a geometric objects, such as the determinant of the matrix and Ricci curvature. And this makes the relationship coordinate independent or truly covariant and links thermodynamics directly to the underlying spacetime geometry. And so if we integrate this in respect to a proper time, we get this interesting result here. And this acts as an observational signature of Ricci Flow-like processes. And it parallels the Einstein-Hilbert action. And it directly measures how much excess curvature is generated by non-equilibrium states, making Ricci Flow potentially detectable through this geometric or energy-based indicator. And so in other words, Ts divided by ET is the observational indicator, which directly relates to the amount of excess curvature from the equilibrium or GR solution. In other words, the surplus curvature is caused by non-equilibrium states. And essentially, this connects purely geometric object, the Ricci curvature, to the thermodynamic quantities. And in essence, the thermal equilibrium at the macroscopic level provides the local properties, while at a hydrostatic equilibrium, this ties the local properties together across space under the influence of external potentials. And so a photon gas or a purely free energy state would reach local equilibrium distribution very rapidly via the radiative process because it's propagating out at the speed of light and it's going to reach equilibrium very quickly. But an overall distribution of the gravitational field must also adjust to this hydrostatic balance. And so high entropy particles colliding may reach some common temperature locally or spread out and concentrate in a way that the free energy is minimized globally. And so what this kind of this here relates to a relationship between the free energy and the total energy, resulting on how sharp essentially these gradients are from the Ricci flow. And so that's what's providing that kind of observational ability. And so this essentially is a statement about how fast, or a statement about how the state of energy directly affects local curvature. And so while the aggregate or average description may be similar or identical in both cases, the local conditions are not. And this affects on how we observe them and how we observe systems. And so while the macroscopic description of these two piles, one with like coarse sand across some surface and one of a dense ball of the same mass, the local deformation is going to be related to, the surface tension and the mass concentration. And high complex particles with high degrees of freedom directly relate to high entropy states. And so we can talk about the amount of local perturbation versus the global stretch. And so as such, we can kind of get a measure of effective curvature, and we need to incorporate this non-equilibrium curvature through some kind of weighted sum, which I just proposed here. And the traditional Einstein-Hilbert action can be updated to reflect this. And in doing so, we can reconstruct the modified field equations and look at, the strong field limit and the weak field limit. And we can find that we are compliant with general relativity for almost all observations. For instance, within our solar system, despite our sun having very high temperature, it has very low entropy. It's highly homogeneous. Essentially, the sun is a giant ball spewing high levels of free energy in all directions. And as such, hydrostatic equilibrium would be reached very quickly anywhere near such a system. And so these systems are all over the galactic plane. And from that, we simply recover out the Einstein-Hilbert action because the temperature entropy contribution essentially goes to zero, and we just recover out the standard traditional Einstein-Hilbert action. But in black hole dynamics, this provides an adequate correction to avoid the singularity paradoxes. Additionally, that one might ask, what about far away from the galactic plane, say in a dark matter halo, for instance? Well, these halos are actually characterized by high temperature and high entropy gas clouds that have very low free propagating energy transiting through them. And as such, you should expect higher curvature in there. And this is somewhat interesting because we only define dark matter from what's called the virial mismatch. We essentially say that we observe these gases that have higher kinetic energy than their potential should bind them to. And so therefore there must be some missing curvature or missing mass. And my argument is the exact opposite, is when you spot a virial mismatch such as that, that is actually indicative of an inequilibrium state, and you should expect higher curvature as a result. And so specifically, if you build a toy spherical model, you get three specific regions. You get a core region, which is near radiative sources, which exactly fit the GR solution from Einstein, flat or no added curvature. You get a transition region, such as in between spiral arms or just outside the core, which ends up falling off as a 1 over r fall off according to the Ricci Flow dynamics. And then you get the drop off region, which extends out into the vacua, which falls off as 1 over r squared, then over 1 over r cubed, and then eventually exponential decay. And these three regions actually almost exactly match the NSF profile for dark matter, which is kind of interesting. And so, yeah, so there's not only is this just kind of an interesting idea, it actually offers some predictive capabilities, which is interesting. By modeling black hole singularities in this way, we drive out this equation, which also happens to explain um, uh, dark matter as a form of, or as a result of this modified action. There's some cosmological principles, as many of you know. Lambda CDM is essentially dead, and we already have talks about various different, models that could potentially recast this or adjust it. Particle physics for quantum chromodynamics. I actually have a paper in preprint on arXiv examining if we can kind of use this methodology to examine containment in a geometric way. And there's also implications to superconductivity in the way that we kind of see spontaneous symmetry breaking occurring as related to this directional bias. And that's the end. Here's some of my references that I used. I'll just go through. This is being recorded, so if you guys are curious, you can go through the recording and find the reference that you want. And that's it.